Now, may I request our last speaker, Amaury Micheli, to share his screen?
Yeah, okay, thanks.
Yes.
Can you tell me if it works?
Yes, your screen. Maybe you can go to full screen.
Okay, yeah. Is that all right?
Yes, now it's visible. Thank you.
Okay, can you also hear me clearly? It's not.
I can hear you. I can hear you.
Okay, wonderful, wonderful.
So I'll warn you. I mean, tell you around 10 minutes, and then. Okay.
Around 10 minutes? You mean around
yes.
certainly?
I'll tell you in 10 minutes, and then you can wind up in 2 minutes, 13 minutes, right? 3 minutes.
Right.
Okay.
Okay, so we agree it's 15 minutes, right? In total.
Yes.
Yeah, okay.
You can tell you can wind up in 12, 13 minutes.
Okay, sorry. Okay, very fine. Okay, thank you very much. So, hi everyone, it's a real pleasure to be here at this very nice conference, and I'd like to thank the organizers for this nice symposium, and also for giving me this opportunity to present my work to everyone today. So I'll be telling you about the work that we've conducted with Jérôme Martin and Vincent Venin on the computation of quantum discord of inflationary perturbation in the context of decoherence. And this work will be based on a paper we've put on archive a few weeks ago with this reference here. So if you like the talk, you can check out the paper later. So before I dive into the technical details of what is quantum discord, what is decoherence, I would like first to give you some motivation for this work. So our idea is to look at quantum features in the early universe. So I'll try to motivate why it's interesting and where are these quantum features. So the idea is that if you look at the early universe, you probably know that it's very homogeneous. For example, if you look at the CMB map by Planck, you'll find that the temperature and isotropies will be only of the order 10 to the minus 4, for instance. But still, it's not completely homogeneous, right? So you may want an explanation for the presence of these inhomogeneities. So where do they come from? So already in the 80s, there was a proposition that these inhomogeneities could come from minimal vacuum quantum fluctuation that are then stretched to cosmological distances by expansion. And this proposition is quite intriguing because it puts in tension two things, right? Quantum fluctuation, so something that you typically expect on very small scale, and anisotropies that you see in the CMB map, which are on cosmological scale. So you may wonder at first, well, when you see that the first time, is it very serious? Can this be a viable proposition to describe physics? And actually, yes. For example, we already have an indirect proof that this scenario is quite consistent, because if you compare the prediction for such a scenario for the power spectrum, and you compare it with the observational data of, let's say, Planck, you have in blue the prediction here, and in red the observational data points by Planck, and it matches very well. So, okay, we can take this scenario of initial quantum fluctuation seriously and say, but then you have to answer another question, because you have something which is quantum at the beginning and then goes to cosmological scale, so you expect it to be classical now. Then how and when this transition happens? And this is exactly the kind of question that motivated our work. And if you want to try to answer it, then you need at least two ingredients. You need first a way to measure the quantumness of your state. And this is what quantum discord is made for. And you need also a mechanism to explain this quantum to classical transition. And this is exactly what is decoherence. The idea is that when a quantum system is interacting with extra degrees of freedom, it will tend to classicalize. So I'll now describe exactly in more technical details what is quantum discord and what is decoherence. And I'll start by this idea of trying to characterize the quantumness of a state, and the quantumness in particular of inflationary perturbation. So in general, if you want to characterize the quantumness of a state of the system S, what you can do is take your system S and split it into two subsystems, S1 and S2, and look at the correlation that exists in between these two subsystems for your state. And you will say that your state is quantum for the system S when the correlation in between the two subsystems are quantum. So for now, this statement, I agree, is quite vague. It's more a paradigm, but this paradigm can be formalized in the definition of the quantum discord, for instance. So here I call the quantum discord D of S1, S2. So I'll give you the technical definition of the quantum discord. It is defined as the difference of two measures of what is called the mutual information between the subsystem S1 and S2. if you want, the mutual information is the amount of information you will gain on S1 by measuring S2. And we have two measures of this quantity here, I and J, and the quantum discord is defined as the difference in between these two. So what is interesting now is that if you consider a system described by classical probability, what you will find is that this difference here, this quantum discord, is always vanishing. But if you look at a system described by quantum state, you can show that this quantum discord can be positive. So here you have a quantity that is 0 if you're described by classical probability, and possibly non-zero if you're described by a quantum state. So that we will take a non-vanishing quantum discord as a sign of quantumness for a state. And this is what you have to remember from this slide for the rest. Okay, so now let's apply that to the case of inflationary perturbation, and first without any extra decoherence phenomenon. So first, I need to tell you what subsystems I pick in my inflationary perturbation. How do I choose the appropriate subsystem to look at their correlation? Well, if you look at the inflationary dynamics at quadratic order, you'll see that what it does is that it creates independent opposite momenta pairs of perturbation. And so what you can do is just take one of these pairs of opposite momenta plus and minus k and consider the correlation in between this plus and minus k modes. In addition, since we work at quadratic order here, we have the nice feature that the state will be Gaussian if you start in the vacuum. And that means actually that it's much easier to compute the quantum discord here. So this computation without decoherence was made a few years ago by Jérôme and Vincent. And what it got is that during inflation, the quantum discord between these two opposite momenta modes here will actually increase to very large values, surprisingly. At the end of inflation, you reach a very large value for quantum discord. And this is something you can remember. Without decoherence, without any extra mechanism to make your system classical, actually the quantum discord is strongly amplified by inflation. And in this sense, the final state could be said to be very quantum with this large quantum discord. So now you may wonder, well, it's exactly the opposite of what we were expecting. So can this result be simply due to oversimplified models? Here we are working at quadratic order, but of course there are interactions. So the question will be, do this result change if you start to put interaction in the mix? So this is what we are considering now using the decoherence phenomenon. So for now, we are here. We have a system made of the modes k and minus k, and they exhibit strong quantum correlations. But of course, you don't have only this in the early universe, right? You don't have only these two modes. You have a lot of other modes. For example, even within the same field, we have k prime different than k, and you have a lot of other fields out there. And so all these other extra degrees of freedom, they are an environment for your system. And generally, you expect that if you put interaction between this environment and your system, you go beyond quadratic order. These interactions there, they will destroy the correlation that exists between k and minus k and lead to classical correlation. So this general idea, this general picture is how decoherence is expected to proceed. So now let's be a bit more technical. How do we implement that in general and precisely for inflationary perturbation? So first, you need to model this interaction between your two modes here and your environment. So how do you do that? Well, generally, the first idea you have is just to write an Hamiltonian interaction. So we write an Hamiltonian interaction as some constant of interaction, which is expected to be small, and an integral of products of operators acting on our system times operator acting on the environment. So then with such an Hamiltonian of interaction, you have a couple dynamics for the system and the environment. And if you know what happened in the environment exactly, you could solve. But of course, we do not want to look too much at the environment. What we are interested in is the system only. We don't want to describe all these extra degrees of freedom that are there. So the question is it possible to only consider the evolution of the system? Is there a way to do that? But actually, yes, you have a very powerful tool, which is called the LINBLAD equation, which gives you the dynamics of the system only here, the reduced density matrix describing the state of the system, as a function of commutators of operators acting on this density matrix. So the operators that appear in the Hamiltonian of interaction, but that act on the system only. And here the environment enters in this equation through this autocorrelation function here, that is the 2-point correlation function of this operator here, OE, and through the autocorrelation time. So you have much reduced the knowledge that you have to have about the environment to solve the dynamics of the system. So of course, this LINBLAD equation is only valid under multiple assumptions. So let me detail it here a bit. If you want such a LINBLAD equation, first you need a perturbative coupling, so a constant which is very small compared to 1. You will also need a stationary environment and so for example, a thermal bath. And you will also want your environment to be large enough in a sense so that it's not perturbed by this interaction with the system. And finally, you also want to consider evolution of the system over times that are much larger than the autocorrelation time of the environment, so that the environment somehow can take away the correlation that the system transferred to it. So, okay, now let me show you exactly what we pick for our inflationary perturbation system. So let's say we model our inflationary perturbation using the Muranoff-Sasaki variable V here. What do we pick for the operator OS, for instance? So here, actually, there's a simple choice to make. We take something which will be linear in the field, in the Muranoff-Sasaki variable, because we want to preserve Gaussianity to be able to make simple computation. And we want to preserve the independence of the opposite momenta pairs so that we can split the system into sectors of opposite momenta pairs and look only at one sector. So here OS is linear in V, and you see that due to some normalization and redefinition of the field, you have power of the scale factors that appear in this OS operator. So, okay, the second thing that you need to choose is also the correlation function of the environment. So here we made the simple hypothesis that the environment is correlated over a certain physical length LE, and that beyond that, you have no correlation inside of the environment. So we model that using...
Amaury, you have roughly 2-3 minutes.
Okay, I'll run that up. Okay, so you have this correlation of the environment, which is modeled by a top-hat function, where you see again, because we use moving coordinates, scale factor appearing. So, okay, all in all, you take that, you put that into your LINBLAD equation before you transform and look only at the plus and minus k sector. And what you get is an equation for this plus and minus k sector, where you have again your commutators here, you have the top-hat function, and you have a lot of factors that came out from all this transformation in France. And this can be simply summarized as an overall interaction constant, which is not time dependent, which is k gamma, and also scale factors that comes from the different points that I've stressed. So you have a time dependence here in A, the scale factor. So here will be 2, but actually we work with a slightly more general fit model where we say maybe G will be time dependent, maybe the autocorrelation function will be time dependent as well. And so to account for this time dependence, we put an arbitrary power of the scale factor P here. And we have only these 2 free parameters in our system, an overall K gamma and a dependence on the scale factor to the power P minus 3. So 3 parameters. Okay, now the question is, with such a model, what happens to quantum discord at the end of inflation? Is it destroyed by decoherence? Okay, so actually what happens is that it depends. It depends on the value of P and K gamma. This is not black or white. So here you have a discord, which is when you have blue here, it means that the quantum discord is very small. When it's red, it means that the quantum discord is very strong. So here, for example, if you have a small dependence on the scale factor and a small K gamma, you will have still a very large quantum discord after 50-fold inflation here. But on the contrary, if you have a P which is quite large, you can have no decoherence left. So the result here is that you have actually a competition between 2 phenomena. You have first the inflation that builds up entanglement and generate quantum discord that we have discussed before. And now with this decoherence phenomenon, you can try to remove some of this correlation, but depending on how strong it is, you must still have some quantum discord at the end. So you have this competition here that determines the fate of the quantum discord and hence of the quantumness of your system in a sense. So let me just to finish by giving you some future direction for our work. What we like to do is to compare the effect of this decoherence on different criteria, for example, Bell inequality and non-separability, and see if we recover similar results. And also move to a more realistic interaction for decoherence, for instance, using non-linearities of pure gravity, and again, see if that changes the results. So thank you very much for your attention. And if you have any question, I'll be very happy to answer.
Thank you very much, Amaury. We have time for some questions. I believe Sayantan Chowdhury has a question. Sayantan?
Hi.
Thanks for the nice talk. You have mentioned about some environment. So are you considering some kind of open quantum system in this description?
Yes, exactly. That's a bit the idea. It's exactly the idea of the LINBLAD equation.
No, yeah. So then my question is like, so what kind of, because even the environment is not important, you are interested in the subsystem dynamics. So this LINBLAD equation is basically giving you a non-unitary time evolution.
Absolutely.
It's a kind of non-unitary time evolution. Now the problem is what kind of system it is. Like I just want to understand, because is it a Markovian system or non-Markovian system? Because why your LINBLADian operator is so simple? That's my question.
So first, just to tell you that it's not completely ad hoc in a sense, this model here, you can see that this equation here, you can get it for p equal 5 using an interaction model where you have an action where it's an interaction between a light field and an AV field. And then you can check that if the field is AV enough and the interaction constant is small enough, all the assumptions that I've laid out for LINBLAD are actually satisfied. Okay.
No, and that's okay, but I'm just saying that it has some kind of memory or without memory.
No, exactly. I'm not sure because I'm not really specialist of these details, but I think that behind this idea of looking at the time evolution of the system being much larger than the autocorrelation time, I think you can think of that as some kind of memoryless environment, some kind of Markovian assumption here.
If it is a Markovian, then it is very complicated. That's why I was worried. If it is a non-Markovian, then it is okay.
Okay.
And if it is Markovian, then tracing out the environment degrees of freedom and doing the path integral over that is extremely complicated. And it is very, very model dependent. Means there you have to, in very specific kind of environment, you can do the calculation analytical. So that's why I was very worried that what kind of environment you are talking about, because you didn't mention about explicitly what the environment is. If it is a non-Markovian system, I am completely okay with the calculation. But if it is a Markovian system, then it is like the form you have written, I just didn't understand like what is exactly going on. Okay, you may think about this. You may think about this.
To be fair, I don't know if it's Markovian or not, because I just know the assumption that I need to derive the LINBLAD equation which are there. So maybe my statement saying that this means Markovian, it is completely wrong. So thank you for your comment, and I'll look into that.
Okay, thank you.
Thank you, Sayantan. Are there any other questions?
I had a question, Srinath, but it was partly answered in response to Sayantan's question. Yeah, thank you, Amaury.
So let me thank Amaury again and all the other speakers of the session.